On January 17, 2008, a mysterious failure caused the British Airways Boeing 777 to come crashing down just short of London's Heathrow Airport. This was the first full loss of a 777 aircraft, which had been operating without serious issue since 1995. In a strange twist, the culprit in this accident seemed to vanish after the crash, leaving investigators puzzled. Speculation was rife after the accident, with some saying that a software glitch may have downed the aircraft, or that there may have been radio interference from the Prime Minister's motorcade, which was passing nearby at the time. In the end, investigators found that the cause was both far simpler and far more pernicious. What follows is the curious story of British Airways Flight 38, the flight that showed how a collection of circumstances, which in their own are harmless, can combine to cause an accident. This is also the story of how experience and quick thinking can be the difference between life and death. At about 10 AM local time on January 17, 2008, British Airways Flight 38 pushed back from the gate at Beijing International Airport in China. On board were 136 passengers and 16 crew. The flight was bound for London's Heathrow Airport in England, a 12-hour, 8,000-kilometre journey. In the cockpit on this flight were 3 experienced pilots. Captain Peter Burkle was 43 years old and had 12,700 hours of flying experience under his belt, over 8,000 of which were on the 777. He doesn't know it yet, but in 12 hours he will draw upon this experience to save his own life and the lives of everybody else on board the plane. In the right-hand seat was the senior first officer, John Coward. He was 41 years old and had 9,000 total flying hours, 7,000 of which were on the 777. The other pilot, First Officer Conor McGuinness, was 35 years old and had 5,000 hours of flight experience, just over 1,000 of which were on the 777. The presence of 3 pilots on this flight meant that each of them could take a 3-hour break at some point during the cruise, ensuring that they would all be well rested for the approach into London. The aircraft being used for this flight was 7 years old and had entered service with British Airways in 2001. The 777 was and still is a highly modern aircraft with an excellent safety record. Up until this flight, not a single 777 had been lost in the aircraft's 13 years of service. Flight 38 lifted off the runway at Beijing at 9 minutes past 10 local time and headed northwest towards London. It was carrying 79,000 kilograms of fuel for the long journey. The aircraft's flight plan required it to climb initially to 10,400 metres, or about 34,000 feet, before descending back down to 31,500 feet because of the extremely cold air at that altitude. The air at altitudes used by commercial aircraft is normally very cold. Typical temperatures lie between about -40 and -57 degrees centigrade. On this day, however, conditions were unusually cold, with temperatures as low as -76 degrees centigrade or -105 degrees Fahrenheit. Nonetheless, air traffic control asked the crew if they could climb to about 35,000 feet. The crew accommodated this request and monitored their fuel temperature closely. They knew that they had to ensure that the fuel did not come within 3 degrees of its freezing point, which was -47 degrees centigrade. Even though the outside air was much colder than -47 degrees, the temperature experienced by the surface of the plane, and thus the fuel, was much higher. This is because the friction of the fast-moving air heats the surface of the plane, raising its temperature substantially. At the speeds commercial aircraft travel at, this friction increases the temperature experienced by the plane by about 30 degrees centigrade. As Flight 38 continued across Siberia, it eventually burned off most of its 79 tons of fuel, making it light enough to climb to 40,000 feet. The pilot selected the vertical speed mode of the autopilot and set it to climb at 400 feet per minute until it reached 40,000 feet. It stayed at this altitude until approaching the coast of England from the North Sea. At 2 minutes past noon local time, the pilots began their descent towards London. They first levelled off at 11,000 feet and entered a holding pattern to the northeast of London. They spent 5 minutes in this holding pattern and continued descending to 9,000 feet during this time. They then received radar vectors from air traffic control to line up with runway 27 left at Heathrow. A few minutes later, the pilots were lined up with the runway on final approach. They had the aircraft fully configured for landing at 1,200 feet, with the gear down and the flaps extended to 30 degrees. The autopilot was flying the aircraft at this point, and the autothrottles were controlling the engines. In a few seconds, things would start to go seriously wrong. The autothrottle made some minor adjustments to the engine thrust, increasing and then decreasing it again to maintain the aircraft's final approach speed of 135 knots. However, during one of these increases in thrust, the right engine did not respond. Rather than increasing its thrust in response to the autothrottle command, its thrust actually decreased. 7 seconds later, the left engine experienced the same problem. The aircraft was merely 600 feet above the ground at this point, and less than a minute from touchdown. At this point, air traffic control then cleared the aircraft to land.
Speedbird 38, clear line 27 left, the wind 210 knots. Clear line 27 left, speedbird 38.
The first officer, who was the pilot flying, noticed that the thrust levers were uneven, with the left lever leading the right. Several seconds later, the autothrottles moved the thrust levers to the full forward position, as they realised that the engines were not producing the commanded thrust. When the aircraft was 430 feet above the ground, the captain made the standard call out of "stable," indicating that the approach could be continued. However, the co-pilot replied, "just." 7 seconds after this, the co-pilot said, "What's happened to the speed? Yeah, but look, what's going on?" He pointed to the thrust levers, which were commanding full thrust, and yet the engines were barely at idle power. He pulled the thrust levers back and then pushed them forward again, but nothing happened. The relief pilot sitting in the jump seat behind the pilots said that it looked as if both engines had failed. However, this wasn't the case, and so the pilots couldn't perform the double engine failure drill. The aircraft was now over a mile from the runway, and it was losing speed and altitude. If the pilots couldn't get the engines to produce more power, they could crash into a housing estate just short of the runway. The captain quickly scanned the cockpit, looking for anything that was out of place, like a fuel pump that was turned off, or whether the speed brake was extended, but everything was normal. The autopilot tried to pitch the aircraft up in order to maintain its glide path towards the runway, but this decreased the speed further and risked causing the aircraft to stall and fall out of the sky. At about 240 feet above the ground, the airspeed had decayed to just 115 knots, which was well below the target approach speed. The aircraft was now falling rapidly towards the ground, with a descent rate of 1800 feet per minute, more than double the usual rate. The crew had to act fast to salvage the aircraft. The captain drew on his experience to make a number of bets that he thought might reduce the number of casualties. First, he let the first officer continue flying the aircraft, as he was highly experienced, and this would give the captain himself time to find other ways to save the aircraft. He knew he had to reduce the amount of drag on the aircraft in order to extend its gliding distance so he could crash within the airport perimeter. He kept the landing gear extended, as even though these increased drag significantly, he knew they would absorb the brunt of the impact forces. However, he reduced the flaps from their current setting of 30 degrees to 25 degrees. The hope here was that this small reduction in drag would enable the aircraft to fly far enough to avoid hitting the buildings short of the runway. This had an immediate effect. The aircraft's rate of descent went from 1800 feet per minute to 1400 feet per minute, and it then became obvious to the crew that they would clear the buildings, and that they would probably crash down within the airport perimeter. The captain would later say that in this moment, his estimation of the death rate among passengers went from 100% of passengers to about 50%. The speed of the aircraft was now 108 knots, and the stick shaker activated, indicating that it was close to stalling. The first officer pushed the nose down slightly to stop the speed decaying too much. There were now 10 seconds until impact, and the captain realised that the last thing he could do to improve the survivability of the accident was to make a mayday call to air traffic control.
Mayday, mayday, speedbird, 95.
The aircraft impacted the ground hard, about 330 metres short of the runway threshold. It bounced into the air and then hit the ground again, this time sliding uncontrollably along the ground. It came to rest a few seconds later, just 372 metres from the first impact point. Here's the air traffic control audio from immediately after the crash.
229, hold position. Aircraft accident. The position is the threshold, runway 27 left. Aircraft type is a 777. Natural problem is crash. Aircraft has crashed. Rendezvous point is south. Qatari 01. Mr. Captain, this is an emergency. Evacuate. Transmit on ATC, sir. Fire service on the way. Qatari 011, go around, I say again, go around, acknowledge. Qatari 011, go around. Fire 2 is on the runway. I can confirm, shoots have been deployed. Copy, sir.
Incredibly, all 152 passengers and crew survived the crash. There was just one serious injury. One passenger's leg was broken when part of the landing gear breached the fuselage during the crash sequence. Investigators got to work immediately after the accident. In the absence of any obvious cause for this sudden loss of engine thrust, the media went on a speculation frenzy. How could an accident like this happen to British Airways, one of the safest airlines in the world, and to the Boeing 777, one of the safest aircraft in the world? Indeed, this was the first time a 777 had been written off due to a crash since its introduction 13 years earlier in 1995. With hundreds of these aircraft in passenger service around the world, should this incident be cause for concern? Initially, everything was on the table as a possible cause. There was speculation that the highly automated systems on the 777 had malfunctioned due to a software glitch. There was even discussion around the idea that the Prime Minister's motorcade, which was passing nearby at the time, had interfered with the aircraft systems and caused the loss of power. However, when investigators turned their attention not on the flight's final few minutes, but on the hours leading up to the crash, they discovered something unusual. On first appearances, the flight had been completely normal up until the final few seconds, when both the engines failed to produce the required thrust. However, after looking a bit closer, investigators discovered that there were a few ways in which this flight was a statistical outlier. Investigators examined data from 178,000 flights by Boeing 777s and found that this flight was unique in that it had a combination of a low fuel flow to the engines during the cruise phase of the flight and a high fuel flow during approach while the fuel temperature was low. The majority of flights had a higher flow of fuel to the engines during the cruise and a higher fuel temperature on final approach. The reason this flight had a low fuel flow during the cruise is that when the pilots made a number of step climbs up to higher altitudes throughout the flight as the plane got lighter, they did this using the vertical speed mode of the autopilot and commanded a slow rate of climb of just 400 feet per minute. This slow rate of climb meant that the engines did not need to significantly increase their fuel flow in order to accomplish the climb. This meant that naturally occurring ice crystals in the fuel had been able to accumulate in the fuel pipes without being dislodged. Normally, the commanded rate of climb would be higher, or pilots would use the VNAV mode of the autopilot to accomplish the climb, which would typically command a higher thrust setting. Then, on final approach, the fuel temperature on Flight 38 was minus 22 degrees centigrade, which is unusually low for this phase of flight. This was because the aircraft had been flying in unusually cold air for the previous 11 hours, and the fuel temperature remained well below freezing throughout the flight. This meant that any ice which had been accumulating in the fuel lines during the flight remained there even during the approach, when the fuel would typically be warmer. This ice occurs naturally in fuel, and so it should not have been a problem for the fuel system. However, the fuel temperatures during much of the flight were in the so-called sticky range, where ice crystals are most likely to adhere to their surroundings. During the initial descent, the engines were on low power, meaning that the fuel flow was low, and this ice remained stuck to the fuel pipes. However, when the plane was on final approach and there were engine accelerations, this increase in fuel flow dislodged the ice, causing it to flow through the fuel system and form a restriction on the face of the fuel oil heat exchanger, pictured here. This blockage was enough to significantly reduce the fuel flow to the engines, causing the reduction in thrust. Here's a picture from the final report into this accident, which shows just how unusual this particular set of circumstances were on British Airways Flight 38. Each of these dots is a flight conducted by British Airways 777. The vertical axis shows the amount of fuel delivered by each main tank, which is below 20 degrees centigrade, and with a maximum fuel flow of 10,000 pounds per hour. In other words, Flight 38, which is the outlier at the top of this graph, consumed about 25,000 kilograms of fuel from each tank at minus 20 degrees and at a maximum rate of 10,000 pounds per hour. The takeaway from this chart is that it is highly unusual for a 777 to consume this much cold fuel at this lower rate of fuel consumption. In these very specific and unusual conditions, ice may build up in the fuel lines, and when engine thrust is increased closer to landing, it may be dislodged, where it travels through the fuel lines and causes an obstruction at the fuel oil heat exchange. The certification requirements for the engines and the fuel system did not require them to be invulnerable to this phenomenon, as it was simply not known about at the time. As a result of this accident, Rolls-Royce, the manufacturer of the engines, changed the design of the fuel oil heat exchanger so that it was less vulnerable to ice build-up under these conditions. Boeing also recommended that if pilots suspect a fuel icing problem, they should bring the thrust back to idle for 30 seconds, then increase the thrust to clear the blockage. This could not have been done on British Airways Flight 38, however, given how close it was to the ground when the loss of thrust occurred. In the end, it was miraculous that this flight ended as well as it did. A near total loss of engine thrust on short finals is a life-threatening situation, and the quick-thinking actions of the flight crew saved many lives on board. After the crash, Boeing test pilots spent months recreating the landing in a full-motion Boeing 777 simulator, and were unable to achieve a further glide than was achieved by the pilots on this day. Since these changes to the design of the fuel oil heat exchanger, there has not been another similar accident on the Boeing 777, and it remains to this day one of the safest passenger aircraft in the sky.